All right. Just so you guys know, I'm recording this so that if Madison wants to go back and watch it, she can. So I will leave that up to her. So. Yeah. All right. So yesterday we talked about the idea of the electric field, and we kind of introduced the idea of field theory, and we had to come up with a way to explain how these charges can apply forces to each other, even though there's no direct contact. Okay. And we talked about the idea that, and I'm going to write this with my mouse, so here, when we talk about the field, we talk about a force per charge. We use Q to represent charge. So the field, which we usually represent, totally forgot my word there. We usually represent that with the capital E, is represent the force divided by the charge. Okay? So, going back to this simulation, and Sean, I know this one's boring, but we'll go so. Alright, so I'm going to start off and I'm going to take one of these positive charges down here at the bottom. Okay? Oh, can you see it? Oh, so I'm going to take one of these positive charges here on the bottom, and I'm going to place it just out here into the field, and these arrows show up. Okay? So, let's talk about two things that you notice about the arrows. Okay? Okay, they all point out, and what else? They're stronger in the center, and you know that because what do you see about the arrows as they get farther and farther away from the charge?
They're not as vibrant.
Yeah, they're like fading, right? So in this case, the arrows are going to represent the direction of the field, and then the strength or the darkness of the arrow represents its magnitude. Field is a vector quantity, okay? All right, so let's get rid of that one, and let's put this negative charge out there. Okay? They all point towards it, okay? So that being said, the description of the field is going to be based on the behavior if we put what in that space. What kind of a charge? Well, according to this, if all of these arrows point towards the negative charge, that's what would happen to what kind of a charge? A positive charge, right? And if we put this positive charge out there, all the arrows point which way? Out, which is what would happen to what kind of a charge? A positive charge. So we describe the electric field based on what would happen to a positive charge in that location, right? So when we take this out here, this yellow one, right, that red arrow would represent what? The force, right? That's the force that charge, so that means that the sensor represents what type of charge? A positive charge, right? And as we move further and further away from that red charge, what force gets smaller, right? And as we get closer, force gets bigger, right? So that red arrow is representing the force that charge feels in that location. Okay? Good? So we start our discussion of charges with just a single point charge. But we can obviously add multiple charges. So if we take another red charge and put it right on top of the original red charge that we have, right? Nothing changes with the direction of the field, but it's a lot stronger. It's a lot stronger farther away from that charge. And if we take that charge away, right, it goes back to the way that it was. If we have two charges that are not right on top of each other, now we start looking at vector sums, right? The sum of the two vectors of the two fields, right? And as we move this around, you can see the direction of the field changing based on the combination of the two arrows, right? One thing we'll always see, though, is we generally speaking refer to these arrows as field lines. And a lot of times you'll see them actually connected around each other so that they kind of start and end in the same spot. But the arrows are always going to point away from positive charges, regardless of how many positive charges we have. Right? Arrows always point away from positive charges. Okay? But if we throw a negative charge in there, so first I'll throw this positive charge out here, then I'll throw this negative charge over here, right? You can see a pattern developing where the arrows all start at the red and end up at the blue, right? Because that's what would happen to a positive charge in that setting, right? If I took this blue charge out and replaced it with a red charge, right? There's a spot in the middle, right here, if I can get it right, right? Where the forces cancel out. Well, actually, the fields cancel each other out, right? But that, yes, the forces are equal, and this, you got to get it right. But yeah, there is a spot in there where we could have zero field, which would mean no electric force.
So tired.
All right, we're back. I paused the recording when they came in. Now we're back recording. So. All right, is that good there as far as these fields go?
Yeah.
Okay, so let's try another one. All right. So here, let's go back to, so now, all right, we're just talking about vector sums there, okay? All right, so let's go back to the list of simulations. Easy. All right, let's go back to the list of simulations. And if you go about to the fourth row down, there's one called Electric Field Hockey. John Travoltage. We'll talk about John Travoltage later on. So, this is a Java application, so you have to it opens up down at the bottom. If it asks you to update the Java, just say you'll do it later. So, Electric Field Hockey.
Actually, we used that last simulator before.
Just to demonstrate stuff. So, all right. Are you up yet or no? Yeah. So, I hope it doesn't, because that's my computer I use in the IB office. So I hope it doesn't. Not a desktop, no. So, I kind of don't want a desktop. I mean, I take that home with me, and I didn't see them. Nobody was sitting in your spot, though, if you want to check up there and see if it's... Yeah, I didn't see them, though. Sorry. Kidding me. Ridiculous. All right, do you guys want to come up here and do this? You can come up here and play. So, all right. First, I'll just do this quick demo. So, that's why I went and checked the Chromebooks, and the Chromebooks don't have Java either. But it's like the last simulation we did, the field one, was just an HTML application, so you can run it through Chrome. But this one is a Java application. They haven't updated all the Java applications yet to run on HTML. So. Anyway, all right. So here's the gist of today. Just we're gonna mess around with it a little bit, right? Like it says, field hockey. Here's the puck. Here's the goal. All right. Based on adding positive or negative charges to the arena, you're trying to score a goal. Okay. This is the practice. All right. So if I take this positive charge and put it right here, right? Okay, it kind of gives you this,
cool.
and then you hit start, goal. Okay,
And then you get the next level.
Okay, so then we reset
Kind of reminds me of
okay.
Velocity Raptor
a little bit. So, and then we could also put like we can put negative charges in places, right? Okay. I don't know if if it's too far away. Okay, so we can get goal there. Okay.
Start zooming.
All right, so that's the practice. Okay. Oh, other things we can do. Okay. If we want to, we can turn on the field. Okay. That might help a little bit later on.
Cheating, Mr. Fox.
Well, you'll see that might help you a little bit later on as we increase the degree of difficulty. Okay. You can also, if you check this one down here, the trace, it will show you the path of the puck. Not really exciting in this one, but that might help you a little bit later on. Okay. So that being said, if you go down here to the bottom, you'll see that difficulty 1, 2, and 3. Difficulty 1 starts adding obstacles in the way, like this wall. Okay. So your goal is to put charges in different places to create a field where this object will be able to navigate its way from the start to the goal. All right?
It's pretty simple.
Good there? All right, well, let's start messing around. So I'm going to stop this recording because that's really all I wanted to talk about today.
All right.
And then we can start messing around and you guys can see how it works and see how well we do. So.